Welcome to Study Loop.
So in part A, we need to find out the angular momentum with respect to point O. Now we see that point P is where the rock is, and then there's a horizontal velocity in which is denoted by the green arrow. The distance from P to O is 8 meters, and the angle that this radial vector or this PO line makes from the horizontal is 36.9 degrees. Now, if we draw a free body diagram of this system, we see that this is the rock, and from point O, since we are trying to find out the angular momentum with respect to point O, so we can consider that as our axis. So our radial vector points towards P, so that's why there's an arrow directing towards point P or directing towards the rock. Then we have the velocity, and since the rock is in air, so mg is acting downwards. Now we see that since this line and the green line is parallel to each other, so that's why this angle is equal to this angle. So that means this angle right here, we call it phi, should be equal to 180 degree minus 36.9, which is 143.1 degrees. Now we'll talk about in a second what this part means, but let's see what we need to do to find out the angular momentum. We know angular momentum is mvr sine phi, where phi is basically the angle between the radial vector and the velocity. Now we can extend this radial vector in this direction because um, at this point, if we say this is the point of our origin, then the radial vector is going away from there, and then our velocity vector is this way. So we need that here because again m times v phi is 143.1 degrees. So if we put all the numbers here, we see that L is 115 kg meter square per second. Now the reason we are calculating this part is because we know that for the angular momentum, how do we get this formula? So we should always remember that for the angular momentum and radial vector should act perpendicular to each other. So momentum and radial vector should act perpendicular to each other, or in other words, only the perpendicular component of the radial vector will have an effect on the angular momentum. So that's why we're taking the perpendicular component of this r vector, which is r sine 36.9, and it turns out that this is equal to r sine phi. So that's why we are considering L here, where we could have also written that in terms of mvl. So yeah, that's how we got the angular momentum. Now what about the direction? So for direction, we always start with the radial vector, and so we'll use the right hand rule for that. So we'll start with the radial vector r, so let's call that r, and then we curl our fingers towards v. So if we do so, we see that our thumb is pointing towards, or our thumb will be pointing into the page. So that's the direction of our angular momentum. So angular momentum will have a direction into the page. So, and in part B, we have to find out the rate of change of angular momentum, and it's nothing but the torque, because torque is, in other words, torque is rate of change of angular momentum. So to figure out torque, we can again go back to this picture where we have to take the com component of the radial vector, which is perpendicular to the mg, or to the gravitational force that we have here. So the perpendicular component to mg will be this component right here, which is r cosine 36.9 degrees. So all we have to do is multiply force times the perpendicular component of the radial vector, and that will give us torque. That's what we did here. So we multiplied mg with the perpendicular component. So this is the perpendicular component uh, of the radial vector. And remember this r cosine 36.9 degrees is perpendicular. So this is a perpendicular sine to mg. So only this part will have contribution to the torque. And the reason we're taking this is because the only force that's acting on the rock is the weight. So that's why we're taking the force component, and then we're taking the perpendicular radial vector from the force component. And that's how we figured out r cosine 36.9. So from there we see torque is 125 kg meter square per second squared. Now, what about the direction? Again, for the direction, what we can do is we can use our right hand rule, and then again we curl our fingers from radial vector to mg. And if we do so, we'll curl our fingers this way. And if we do so, we see that our thumb will be pointing out of the page or towards us. So that means the direction of rate of change of angular momentum will be equal same as the direction of the torque, which is towards us, or out of the page. Thank you.